Hi everyone and welcome back to our channel. Today we're diving into the fascinating world of computer science once again, and specifically we're going to focus on processor architecture. Whether you're a budding computer scientist or just curious about how your devices work, this video is for you. Let's get started. Now there'll be a slight difference with this lesson today. As I go through each of the learning objectives, I will be giving you just that little bit more information about each one that you can see on the screen right now. So first up, let's talk about the von Neumann architecture, named after the brilliant mathematician John von Neumann. This architecture is the foundation of most computers today. It uses a single memory space for both instructions and data. This means the CPU fetches instructions and data from the same memory location, one after the other. Now, initially, this seems quite simple, but it does have a bottleneck known as the von Neumann bottleneck, where the CPU can only access one location or one memory location at a time. Next, we have the Harvard architecture. Unlike von Neumann, Harvard architecture uses separate memory spaces for instructions and data. This allows the CPU to fetch instructions and data simultaneously, making it faster and more efficient for certain tasks. You'll often find this architecture in embedded systems and digital signal processing. Now, let's move on to contemporary architectures. Modern processors often combine elements of both von Neumann and Harvard architectures to optimize performance. They use techniques like pipelining, superscalar execution, and out-of-order execution to handle multiple instructions at once, significantly boosting processing speed. Now, for the A-level course, you won't need to be familiar with the superscalar execution and out-of-order execution, but these are there for example purposes, which you are free to search up and kind of research at your own leisure. Now, moving on to CISC and RISC. We want to differentiate between CISC and RISC processors. So CISC stands for Complex Instruction Set Computing. These processors have a large set of instructions, allowing them to execute complex tasks with fewer lines of assembly code. However, they can be slower due to the complexity of the instructions. On the other hand, RISC stands for Reduced Instruction Set Computing. RISC processors use a smaller set of simple instructions, which can be executed very quickly. This simplicity allows for faster processing and more efficient use of the CPU. Let's talk about GPUs, or graphics processing units. Originally designed for rendering graphics, GPUs are now used for a variety of tasks beyond gaming. Their parallel processing capabilities make them ideal for applications like machine learning, scientific simulations, and even cryptocurrency mining. GPUs can handle thousands of operations simultaneously, making them incredibly powerful for specific tasks. Finally, let's explore multicore and parallel processing systems. Modern CPUs often have multiple cores, allowing them to perform several tasks at once. This is known as parallel processing. By dividing tasks among multiple cores, these systems can handle more work simultaneously, improving overall performance and efficiency. This is especially useful in high-performance computing environments and for running complex applications. Let's go back with a bit of history. So early computers were quite limited. They could only perform a fixed set of instructions. Imagine a calculator that can only add numbers. That's how basic early computers were. In the 1940s, pioneers like John von Neumann and Alan Turing introduced the concept of stored programs. This was a game changer because it allowed computers to store and execute instructions from memory, making them much more versatile. The stored program concept is fundamental to modern computing. It means that a program must be loaded into the computer's main memory to be executed. The processor fetches, decodes, and executes instructions one by one. The sequence of instructions can be altered using jump instructions, which are like shortcuts in a recipe that let you skip steps if needed. One of the most common implementations of the stored program concept is the von Neumann architecture. In this design, both instructions and the data are stored in the same memory and transferred using a single shared bus. Think of it like a single lane road where both cars and bikes can travel. This can cause traffic jams or, in computing terms, bottlenecks. An alternative to the von Neumann architecture is the Harvard architecture. This design separates memory for instructions and data, using different buses for each. This reduces competition for the same bus, much like having separate lanes for cars and bikes reduces traffic congestion. The Harvard architecture has several advantages. It allows for different memory sizes and word lengths for data and instructions. This design is commonly used in embedded systems and digital signal processing, where speed is crucial. For example, devices like microwave ovens and digital watches often use Harvard architecture. Despite its potential bottlenecks, the von Neumann architecture is widely used because it simplifies the design of the control unit. Data from memory and devices are accessed in the same way, making it cost effective and less complex to program. This architecture is commonly found in general purpose computers like PCs and laptops. Let's compare the two architectures. So for von Neumann, it's used in PCs, laptops, and servers. There's a shared memory for data and instructions, but there are one bus for both, which can be a bottleneck. The Harvard architecture, on the other hand, used in DSP, microcontrollers, and embedded systems, separate memories for data and instructions, parallel access to data and instructions. Think of von Neumann as a single lane road and Harvard as a multi lane highway. Modern CPUs often blend aspects of both von Neumann and Harvard architectures. For example, desktop CPUs use a single memory but have separate caches for data and instructions. This hybrid approach combines the simplicity of von Neumann with the efficiency of Harvard. Now, let's talk about instruction sets. Complex instruction sets, set computers, or CISC, use a large set of instructions to perform tasks in fewer lines of assembly code. A CISC instruction combines load store instructions with the actual operation. For example, the instruction MULT A B multiplies A by B and stores the result in A. Reduced instruction set computers, or RISC, take a different approach. They use a minimal set of instructions, which are simple, each taking one clock cycle. Operations are performed using multiple general purpose registers. For example, to multiply two numbers in RISC, you would use several instructions as we can see below. CISC has its advantages. It's easier to program with fewer lines of code, and the compiler has less work to do to translate high-level code to machine code. Additionally, shorter code requires less RAM, making CISC ideal for applications where memory is limited. RISC also has its benefits. The hardware design is simpler with fewer circuits, and each instruction takes the same amount of time, enabling pipelining. This leads to efficient use of RAM and software, resulting in better performance. RISC is commonly found in modern smartphones and tablets. Multicore processors distribute the workload across multiple cores, enhancing performance. These are known as parallel systems. Many personal computers and mobile devices have dual-core or quad-core processors, meaning they have 2 or 4 processing chips. Supercomputers can have thousands of cores. To take advantage of multiple cores, software must be designed for parallel processing. For example, browsers like Chrome and Firefox can run multiple processes simultaneously. Different tabs in a browser can be processed by different cores, allowing for smoother performance. A coprocessor is an additional processor that supplements the main CPU by handling specific tasks. Coprocessors are used for floating point arithmetic, graphics processing, and digital signal processing. Graphics cards with dedicated GPUs are a common example of coprocessor systems. A graphics processing unit, or GPU, is specialized for handling graphics and image processing. GPUs contain thousands of small cores designed for parallel processing. This makes them highly efficient for tasks that require processing large blocks of visual data simultaneously. GPUs are not just for gaming. They accelerate scientific and engineering applications and are used in devices like mobile phones, tablets, cars, drones, and robots. For example, GPUs in autonomous vehicles process real-time image data to navigate safely. To wrap up, let's review the key points. Von Neumann and Harvard architectures, CISC and RISC instruction sets, multi-core and parallel processing systems, GPU applications. So understanding these concepts is crucial for anyone studying computer science. Remember, the von Neumann architecture uses shared memory for data and instructions and is common in general-purpose computers like PCs and laptops. The Harvard architecture uses separate memories for data and instructions and is used in specialized systems like embedded devices and digital signal processors. CISC processors use a large instruction set for fewer lines of code, making them easier to program and requiring less work for the compiler. They are ideal for applications with limited memory. RISC processors use simple instructions, each taking one clock cycle, enabling pipelining and efficient use of RAM. They are commonly found in modern mobile devices and tablets. Multicore processors enhance performance by parallel processing, and GPUs specialize in graphics and image processing. These technologies are used in high-performance gaming, PCs, and scientific computing. And that's it for today's lesson. I hope you found this helpful, and I'll see you next time with our lesson on 1.4.